All right, so now let's take a look at the third type of toughening mechanism that I mentioned, and this is transformation toughening. So what this is a stress-induced transformation that impedes the progress of our crack. All right, so again, I've kind of showed you a variation of this for the entire time. So we have, you can think of this as a surface crack of length C, so from the surface to the tip here in this material, and then you can assume that we're applying a tensile force trying to expand the crack tip towards the right. The difference here is that in this ceramic, this matrix, we also have some particles here. So you'll notice these particles. So in this case, these are tetragonal zirconia particles, and these are actually metastable. Excuse me. And so that's going to be important throughout this discussion. So when there's a stress applied, the area around the tip is obviously going to be affected. And so there's going to be a stress-induced reaction where these originally metastable tetragonal zirconia particles in here actually martensitically transform phases. So martensitic because it's very quick, right? And so what that does is when it goes through that transformation, they get bigger, which is what this schematic is trying to show, these particles getting bigger. And when they get bigger, they can create compressive stress. And that compressive stress kind of impedes or blunts this crack from moving further. So the same thing can happen on the surface as well. So that's kind of what this is showing. So anywhere where there's stress, that stress can cause that martensitic transformation. Excuse me. So let's look at the system here. Let's look at the zirconia system. So the idea is that during the cooling of zirconia, we actually form small metastable tetragonal grains. So that's the idea. And so if we look at this system, we notice that at room temperature, the stable phase is actually monoclinic, and it's actually the higher temperature tetragonal that is the phase that's metastable, right? So that's what's happening. We're basically trying to stabilize these higher temperature particles at the lower temperature. That way, the stress can induce the transformation. And there's also a cubic phase, which is worth pointing out. So a lot of what we'll talk about later, it has to do with this cubic phase as well. And so that cubic phase, if we add things, can also stabilize as well. All right, so the stress can induce this martensitic transformation, but also a free surface. So if we have one of these particles on the surface of this crack or at the surface of the material, that can also act as a catalyst for that transformation to monoclinic, because it has kind of free space to transform into the monoclinic phase. All right, so let's look at some of the numbers with the differences between these two. So again, the tetragonal to monoclinic transformation, what that does is it results in a 4% volume expansion. So again, it's causing a compressive stress because of this volume expansion, and it also causes a shear strain, just like a martensitic transformation would, of 7%. And so that also would cause a compressive field in this material. All right, so basically what this is doing and how we can sort of think about this transformation toughening is we can think of it as it reduces the stress intensity at the crack tip by forming this new phase. And so the stress intensity factor at the tip is going to be related to the stress intensity factor minus this sort of shielding factor. And so this is what we're looking at. And so that shielding factor is a result of the So again, I'm not really going to have you use this equation. I just want you to see where some of these terms come in. So we have a dimensionless constant, but more importantly, we have the volume fraction of that phase, the strain. So the larger the strain, the more the shielding factor, and also the width involved in here. So the more we put in, the more strain we have. Obviously, these are better things for this dilution factor. All right. So another thing that can cause this transformation is grinding, surface grinding. So if think about if we have these metastable particles on the surface, if we do any sort of surface modification, that can also protect it. So the act of sort of trying to fix it can also create a compressive stress. So the surface layer tends to also be under compressive stress from those factors, and also that's a free surface, and so those particles can transform easily, putting this whole thing in compression. All right, so one of the systems that we see use this transformation toughening is called partially stabilized zirconia, or PSZ. So what this is zirconia, but it's being doped with either magnesium oxide, calcium oxide, or yttrium oxide. So what that does is, if we look at this phase diagram, over here is zirconium oxide, zirconia. We see the monoclinic phase. We see the tetragonal phase, and we see up here the cubic phase. Well, if we add enough of, in this case, yttria, then we see that 20% yttria, we see this giant region of cubic. So we've essentially partially stabilized that cubic. We've stabilized this cubic form that is usually a high temperature phase. And so what we then do is we stabilize the cubic phase, and we do a heat treatment that allows us to form tetragonal particles, precipitates from that. And then those tetragonal precipitates can transform into the monoclinic phase as a result of the stress. So we do a heat treatment that allows us to do this. Oh, all right. So the next portion the next type of system that uses this is the tetragonal zirconia polycrystals, so TZP. So here, the goal is, so you've kind of, as we've gone through this, you've seen we try to make these little particles of the tetragonal phase, and then their transformation causes these effects. Well, if we can get all of those tetragonal crystals, then that would obviously be good, right? Because then they can all transform and change phase. And so that's kind of what we're doing here, is we have 100% of the tetragonal phase with small amounts of the yttria, and this can give us really high bend strengths and so forth because of this dilution effect. The strain and the amount that we have is very high. All right, so along with that, we can also blend it into other materials, and so that's what we're doing here with zirconia toughened ceramics, so ZTC. This is where we take mixtures of zirconia with these tetragonal particles, and then we finally disperse them in other materials. And that transformation can still occur, but it's doing it in a matrix of some other material like alumina or molite or spinel. And so we can use this transformation in the zirconia system to aid other systems as well. So we're mixing it in with those materials.